Welcome. Today we're going to dive into the invisible shield that protects our entire digital world, the truly fascinating science of cryptography. You can think of it as the art of keeping secrets, and believe me, it's more important now than it has ever been. So, have you ever really stopped to think about that? I mean, every single time you send a message, buy something online, or even just check your bank account, you're putting your trust in the system, hoping your private information stays, well, private. But how? What's really going on behind the scenes to protect all that data? Well, the answer isn't magic. It's actually a powerful science with a really cool history. We're talking about the modern art of secret codes, a field that's come a long, long way from ancient ciphers to become the invisible backbone of our digital lives. At its heart, this is what it's all about. Cryptography is basically the science of taking perfectly readable information, turning it into what looks like complete gibberish, and then turning it back again. It's a whole toolbox of mathematical tricks designed to make sure things stay confidential, and it provides the absolute fundamental tools for protecting data in this digital age.
Okay, so let's actually follow a message on its secret little journey. You can see it right here. You start with plain text. That's just your normal, readable message. Then, through a process called encryption, it gets all scrambled up into ciphertext, which is the secret code that's totally unreadable to anybody snooping. And the only way to unlock it is with the right key, through decryption, which turns it right back into the original message for the person it was meant for.
So, how does this locking and unlocking thing actually happen? Well, it all comes down to a digital key. You can think of it like a secret password that tells the computer exactly how to scramble and unscramble the data. And as it turns out, there are two main ways to handle these keys. All right, let's look at the first major approach. This one is called symmetric encryption. And the name kind of gives you a hint. Symmetric means the same on both sides. And in this case, it's all about sharing the exact same secret key. This image illustrates it perfectly. Think of it like a safe deposit box. Let's say you and a friend have identical keys to the same box. You can put a message inside, lock it up with your key, and then your friend can use their identical key to open it and read it. Simple, right? One key does both jobs, locking and unlocking. So, the really crucial point here is this. For the whole system to be secure, both the sender and the receiver have to have this one single common key. Now, this method is incredibly fast, which is why it's used everywhere. But here's the big catch. How do you safely share that secret key over an insecure place like the internet without someone else intercepting it? That's the key distribution problem, and it is a major, major challenge. And that very problem, sharing the key, leads us straight to our second method. And this is a really ingenious solution that is just fundamental to how the internet works today. It's called asymmetric encryption. Okay, now what's so interesting here is that we're using two different keys. A fantastic way to think about this is like a personal mailbox. It's got that mail slot on the front. That's kind of like the public key. Literally anyone can walk by and drop a letter in, but only you have the special private key to actually open the mailbox and read what's inside. This is the genius behind it all. You can literally share your public key with the entire world, post it on your website, shout it from the rooftops, whatever. People use that public key to send you encrypted messages. But since you, and only you, have the matching private key, you're the only one who can ever decrypt and read them. Pretty clever. Okay, so let's just quickly put them side by side. With symmetric, you get speed and simplicity, but you have that big challenge of sharing the one secret key. With asymmetric, you totally solve the key sharing problem using that public-private pair, but it's a lot more complex for the computer, which makes it slower. This fundamental difference is exactly why they're so often used together to get the best of both worlds. Now, I know this might all sound a bit technical and abstract, but the reality is you use this technology all the time, every single day. Probably without even realizing it. Let's look at just a couple of examples. You know that little padlock icon you see up in your browser's address bar? That's your signal that this amazing cryptographic dance is happening. Your browser uses the website's public key to securely create and share a brand new one-time use secret key. Then, for the rest of your visit, all your data, your passwords, your account numbers, is encrypted using a super fast symmetric key. It's the perfect combo. The security of asymmetric with the speed of symmetric.
And what about when you're texting your friends? When a messaging app says it has end-to-end encryption, it's using these exact same ideas. See, each person has their own public and private key pair. When you start a chat, your phones swap public keys. This lets them encrypt messages that only the other person's private key can unlock. This makes sure that nobody in between, not your internet provider, not a hacker, not even the company that made the app, can read your private conversation.
And that's really what this all boils down to. It's not just about cool math and secret codes. It's about creating a foundation of trust. Without cryptography, our digital world of shopping, talking, and connecting, well, it just couldn't exist the way we know it.
And that kind of brings us to our final thought. As our computers get more and more powerful, I'm talking about things like quantum computing on the horizon that could potentially break all our current methods. The science of cryptography has to evolve right along with it. So it leaves us with a really important question. What will the next generation of secret codes look like? And how are we going to protect our digital lives in the future?